So now I'm just going to talk to you about the computer model which we've developed of the river. So the model is just simply a computer representation of the physical reality. What the model does, it takes terrain data. So we've got LiDAR data, which is collected from an aeroplane. The laser comes out of the aeroplane, hits the ground, and tells us how high, basically the height of the land. We then take hydrological data as to how much rain is falling out of the sky onto the land, and my computer model routes that water as it lands into the river. It tells us how much water is going to flow and where that water is going to go. So we can get estimations of flood depths, flood velocities, and other hazard information we can extract from that model. And so when we build a model, we first try and build that model to accurately replicate historical events. So it's gone through a detailed calibration and validation process where we're confident that the model represents historical events, and that gives us a degree of confidence that we can use our model to forecast what the potential flood extents and depths can be for future flood events. All right, so I'm just going to run you through a little bit of the model which we've built over the past decade or so, actually. So I first started working on the model around 2013, and we worked on that right through 2013 and 14, and it was officially published in August 2015. So that model was formally peer-reviewed, and it was adopted by the Regional Council in 2017. Now that model was calibrated to the best information which we had at the time, which was actually the flood of July 2012. Now that flood was between a 10 and 20 year event. So it was large enough to send a lot of water down the Orowaiti overflow, but wasn't large enough to cause widespread flooding through town. So the new model, which I'm going to be talking about more today, isn't a brand new model, it's simply an upgrade to that model. And if you have been using the data from that previous model or have seen the maps, then just be reassured that there's no major changes to the conclusions. Slight change in flood extent. Some areas the flood depths have come up, and some areas the flood depths have gone down, but that's just due to a refinement of the model and the availability of significantly more calibration data from the 2021 flood. So just in terms of model calibration, I've just got a few screenshots here from the original model, the 2015 model, and these are just screenshots comparing the flood extent from the 2012 model with actual aerial photography which is captured during the 2012 event. So all I'm pointing out here is that the model is able to fairly accurately represent the flood extent. So here's just an image close to the Buller Bridge showing that the model gives a good representation, and here's an image of the flooding around the floating basin and the Lost Lagoon area. Here's an image just showing the extent of flooding down the Orowaiti overflow, and it's just interesting. If you look closely at those photos, you can see that in the aerial photo, that house near the bottom left of the image is flood free. The water's just wrapping around the edge of the land, and we can see the same thing in my image, and we just see little streams of water starting to spill out the overflow, both in the aerial imagery as well as the photo. So this image is simply showing a comparison of the debris level measurements with the maximum water levels which are predicted in the model. And so we use this for calibration purposes, and all this shows is that the model is giving a reasonable representation of the flood depths in comparison to actual measured data. So it's about plus or minus 20 centimetres. The current model which we're using is an upgrade to that model, as I pointed out. It's been upgraded by incorporating the latest LiDAR information, which covers the entire floodplain, which is really useful. We've got very good coverage, and it's current data, so it was flown in December 2020. We've had a cross-section survey carried out by Chris Cole Survey Limited. They're the local survey firm in Westport. That was carried out in 2021 after the flood event, and one of the advantages of the LiDAR was that it was flown at low tide, which has exposed lots of the sandbars in the Orowaiti area. So it means that a lot more information was captured by the LiDAR itself, as LiDAR's unable to see through or penetrate the water. So this image here just simply shows the model extent, and then the yellow box I've put on here just shows the extent of the 2008 LiDAR. So interestingly, the previous model was built on the 2008 LiDAR, which didn't actually cover the full extent of the floodplain. So we had to use much coarser survey information and other data sources to interpolate a terrain outside of that yellow area, which added a lot more uncertainty to the model results. But now with the current LiDAR, which covers the entire catchment, there's much less uncertainty in the predictions. This slide here just shows the 2008 LiDAR, so I just wanted to show you this at the Orowaiti Lagoon area. So as I was saying before, the original LiDAR was flown at high tide, so it didn't capture a lot of those sandbars, etc. in the Orowaiti, whereas the 2020 LiDAR, as you can see here on the screen, there's just a lot more definition. You can see there's a very small river channel running through the Orowaiti and a lot of that sands and silts in the lagoon. So we have a much better understanding of the topography underneath the water. This slide here is just an example of the model calibration. The numbers in the yellow text boxes is the difference between the predicted water level and the measured peak water level after the flood. So we've got about 240 measured water levels or measured debris levels around the catchment, and we've compared those levels and the flood extent with the current model, and we get a very close fit. So this slide simply shows the difference between the measured water levels, which were recorded immediately after the flood, with the predicted water levels from the model. And it shows that we get a very accurate match. So there's some pluses or minuses in there, but the numbers in the yellow text box show the difference. So you'll see some of them are only 3 or 4 centimetres, some are 10 to 20 centimetres. But overall, the model gives an average error of only 4 centimetres, that's 0.04 metres, and an average absolute error of 15 centimetres. And so that's considered to be a very good fit, and it's just showing that the model is able to give a very accurate representation of the flood which occurred in July 2021. Okay, so what I'm showing here is just an animation of the model. So the model's running in real time, and this is the actual calibration event. So this is a really nice way to better understand the flood mechanisms of the Buller River, particularly how the flood occurred in July 2021. So what we see here, it runs for about 1 minute. It's actually showing 48 hours, so 48 hours of actual real flooding time is being represented here in 1 minute, but we can see the Buller River slowly fills up, and as it gets bigger, water starts spilling down the Orowaiti overflow. So we get more and more water spilling out at the top end, heading down into the Orowaiti, and then over time, the Buller River starts filling up as well. And so the first significant flooding of houses that we see, interestingly, comes from the Buller River. So there's a time delay in water going down the Orowaiti and water going down the Buller. So what we see here, the Buller River is just slowly filling up, and water starts spilling over at the floating basin and starts flooding the lower ends of town. And we can see water also spilling down the Snodgrass area. So a lot of water went through that area. So that water slowly backs up, but then the Buller River starts receding. But as the Buller River is receding, the volume of flow coming down the Orowaiti is actually increasing because there's about a 5-hour time lag. The water flows much more slowly down the Orowaiti than in the Buller River. So what we're seeing here is water starts now. As the Orowaiti gets too high, we start getting a lot of water flowing into town from the Orowaiti, from the lower end. And then as the flows get bigger, it starts coming in from the top, out of that Kawatiri subdivision area, as well as from all angles, really. And it just slowly creeps its way up into town. And the peak flooding that was observed during the event was at about 11 p.m. at night, and the model also accurately represents that timing. So the local civil defence controllers have confirmed to me that the flood timing shown in the model matches what they observed on the ground during the day. So the next slide I'll show you is just an image of the calibration for the February 2018 Cyclone Fahey event. So the blue dots I'll show there on the screen were recorded peak water levels picked up by the local survey firm after the flood event, and those red lines in the arrow there was just a sketch made by one of the local Buller District Council staff on paper describing the approximate flood extent and the mechanism, and the model replicates very well with the historic behaviour for the coastal event, with once again a very accurate match with the debris level recordings. So the model has been formally peer reviewed by a professional organisation with no major issues identified. Now this is really important as it just gives us some confidence in using the model for all of these decisions which we're making in the future. So the model's been signed off as being fit for the purpose of setting building floor levels, designing flood protection infrastructure, assessing potential flood mitigations, as well as using the model to assess the impacts of increased future flows and sea levels. So, for example, the impacts of potential future climate change. So I'm just going to show you a couple of shots here of the design maps. So once we have a calibrated model, which has been signed off by a peer reviewer, and we have confidence that the model is accurately able to represent historic events, we then move on to test potential future scenarios in that model. And so what we're modeling here are what we call design scenarios. So this is the 100-year average return interval flood extent using a historic climate. So with the current sea levels and the flood statistics which have been developed with the current data that we have, then this next map shows us what the impact would be for one potential future climate scenario. So this future climate scenario here has been called the RCP6 scenario, and allows for almost 1 metre of sea level rise and an increase in peak flow of about 15%. So it's just a potential future scenario which we can use for planning purposes. Then we've also run the model with, as we know, we're exposed to coastal flooding, so we've run the model with potential future coastal storms as well. So this map shows you the likely flood extent and depth from a 100-year average return interval coastal storm for the current sea levels. And we've actually run the model multiple times with different sea level intervals of 20 centimetres or 0.2 metres, but this map here, which I'm showing you, is potential flood extent for that exactly the same storm, but with the sea level raised by 1 metre. So as we can see, sea level rise of 1 metre will have a significant impact on the town of Westport if we had a 100-year return period coastal storm at the same time. So the key conclusions we can draw from the model is that there is severe flood risk for the entire town. We can have floodwaters coming in from both the top end as well as the bottom end. For medium-sized events, such as the event which occurred in July 2021, the highest flood risk actually comes from the Orowaiti River. However, for really large events, the model starts showing that water starts coming both from the top end, from over the Buller Bridge and over the railway embankment, as well as coming back up in the town from the Orowaiti. And one thing we found in the model is actually a very delicate flow balance between the Orowaiti and the Buller rivers. So the Buller River is pretty much at capacity, and any excess water starts going down the Orowaiti. If we change that flow balance, we're simply transferring risk from one river to another. And so we have to be very careful about anything which we do between those two rivers to make sure we're not just pushing the problem on another section of town. The model shows that lower areas in particular of town are very exposed to coastal flooding. We already know that from what we experienced in 2018, and that's exacerbated with future sea level rise. And another really key point for evacuation purposes is both bridges get cut off once the water gets too high and evacuation becomes impossible, which is one reason why we have to take our civil defence responsibilities and evacuation planning very seriously to make sure that if in a really bad event we need to get out, we're out of the town before things have got as bad as they can get.